Hello, physics. Unit 11, problem 2, Coulombs law. They just attract me in and force me to do these videos. Attraction forces. Coulombs law, right? Attraction between charges, or repulsion between charges, I guess, and the forces that they cause. So, problem 2. 3 charges and a net force. And so I alluded to the first video talking about how you need to let's our plan of attack would be to draw a picture and decide on the way the forces are going to play out, but then use Coulomb's law without positive and negative signs. But then once we get the forces, draw free body diagrams and then figure it out. So what we're going to do here is draw a diagram. That's the first thing we said. So let's do it up here, and we have an origin, and at the origin, well, here's the 0 mark, right? We'll call this the 0 mark. And to this direction on the x-axis, and this is 1.21 meters. And I didn't put negative because it's to the left, so it means on the x-axis over here. So I'm going to draw this charge. It's a positive charge. See it? It's a positive charge. So I'm going to put red for positive. I'm going to put a little positive sign up here. This is a good practice. If you have colored pencils, I would suggest doing red for positive and blue for negative. And so this number is 5.32 times 10 to the negative 9th coulombs. Okay. Over on the other side, we have another positive charge. And this distance is 1.85 meters. Okay, here is this, and we'll put a little negative sign here. There we go. All right, and the charge in the middle at the origin, so that's at 0 here, is positive. So we're going to put that positive. Oh, I didn't put the charge size on this. Oh, wait, this is not negative. What am I doing? It's positive. Oops. See, all 3 are positive. Oops. Sorry, positive. Retraction, positive. So this is positive, so it is 2.25 times 10 to the minus 9th coulombs. Okay. And in the center, it's also positive. And we call that one as 3.22 times 10 to the negative 9th coulombs. So there's your picture. Hopefully you have it. 3 red positives. I don't know if yours are. I think everyone's will be positive, but I'm not sure. They could have a negative in there. So that would change the ending of this story, so to speak. So what one are we concerned about? We're concerned about here. This is our frame of reference. This dot in the middle. Well, how do you know that, Mr. Nishad? Find the net force, free body diagram, yay, on this charge located at the origin. So this is the one we care about. This is our frame of reference. This is our world. Charge in the middle. We'll call that, I'm going to call this A, B, and C, even though they're not labeled that way. But we care about B because they want to know what's happening to B. What's the net force on it? If we cared about A, we would have our whole world centered around that. The calculations would be the same, but we would treat them in a slightly different way. So I know that's counterintuitive, but just let's see the problem and then we'll work through it. And then a later problem will illustrate these issues too, again, to reinforce them. So if we care about B, we need 2 forces. We need the force of A on B. And we need the force, we'll do a different color. Well, let's just do the force of A on B first. And the force of A on B is Coulomb's law, K sub C, Q A, Q B over the distance A to B, okay, squared. So let's fill in there. 8.99 times 10 to the negative 9th. And Q1, or QA, is 5.32 3.2 times 10 to the minus 9 times B's charge 3.22 times 10 to the minus 9 all over, and what's it all over? It's all over 1.21 squared, and that gets us, in my calculations, 1.0518 times 10 to the minus 7th newtons of force. Newtons are left on it. So I left all the units off. They all play nice. I should have checked that. Sorry. Meters play nice. Coulombs play nice. It can't be microcoulombs like in a later problems. It's coulombs. Meters. Check. And coulombs. Check. They all play nice. I should have checked that ahead of time. I did actually, but I just didn't show you that check, but it's important to note. So then it plays nice with the units on KC. And so I left them all off, but I kind of do that sometimes when space is limited, but I always check for dimensional consistency. You have to do that. And in this case, they all play nice. Quote, play nice. Okay, so that's our first charge. That's charge. That's charge. I'm going to put this in. This is F of A to B. Okay? Now let's do, in blue, okay, the force of B and C. Okay. Q, B, Q, C. That order of those two don't matter because it's all commutative property of multiplication. And a rate and the distance between B and C squared, right? Don't forget the squared. 8.99 times 10 to the negative 9. That's a constant. We have B's charge, which is 3.22 times 10 to the minus 9, times C's charge, which is 2.25 times 10 to the minus 9. All over the distance squared, which is 1.85 meters. They all play nice again. All play nice. And when I do this one, I get 8.62. And I took out more on my calculator, so please take out a few more digits than that. I didn't write them down. I apologize. Now, which force is greater? This one here, minus 7th, is greater than, this number is a bigger number than this because a minus 8 is one more to the left, right? Even so, this 8 is bigger than this 1. This minus 7 means you only go 7 to the left when you move this, and this goes 8 to the left. So actually the bigger force is A on B. A and B, the interaction between those two, not the force of B and C. But now, you could say, okay, now it's on to F of A and C. You haven't done those two. Yeah, we don't need it. We're concerned right here, right? We're concerned at point B. And what A is doing to C, if we're holding all of them in static position, not moving, we're saying, or we just take a flash at this instant when they're this distance apart, because obviously if they move, all these forces change quickly with the radius changing. But if so we don't care about the A and C interaction. Now, if we moved our frame of reference over here, oh yeah, we would need that. But we don't. We were caring about B, so we don't care what A is doing to C or how it's pulling on that. So we really don't even need that in this problem. Okay, I want to stress that out. So I'm going to go down here and redraw kind of a little bit down here, and we have our charge here. Okay, this is the middle charge. Now we have this charge over here. This is A, this is B, and this is C. Okay. Now, what is A doing to B? Is A pushing B or pulling B? Well, these are like charges. Like charges repel. Like repel. So A is pushing B to the right. And how big is this force? 1.0518 times 10 to the minus 9th newtons. Well, what is C doing to B? Well, like charges again, but C is pushing B to the left. Okay, and how much? 8.62 times 10 to the minus 8 newtons. So there it is. There's our free body diagram. So what's our net force? Are these helping each other or hurting each other? They are hurting each other. They're not really hurting each other. They're opposed to each other, but I kind of liken it to a tug of war match or a pushing match. Which one is winning and how much is it winning by? If those were two perfectly equal, there would be no one winning. It would be a standstill. So which one is winning? Well, which number is the bigger number? Oh, this is not -9. This is -7. Sorry, people. Double check that. -7. I get a little overzealous with the -9 here because the charges in coulombs are a lot of times that. That's -7. -7. So this -7 means that this is bigger than this -8. So we're going to have a net charge going this way. This is our net force diagram. And what is this going to be? Well, you take this number and subtract this number. Or you can make this a negative since it's to the left and add the 2. In any regard, you end up, when you take this minus the positive of this number, or this adding the negative of this number, you get, oh no, did I, oops, sorry, stop the presses. We're not going to redo this whole problem. I just have a number problem here. There we go. Apologize big time. This number for me, the math is all, the numbers are all okay. I just copied the problem down from my paper incorrectly. And this is 1.90. All the other statements, 1.903, still hold true. So this is 1.903. Everything else I state holds true. So now when you take this number and subtract this, or this number and add the positive of this, you end up with this is the 8.62 times 10 to the -8 newtons. And that is our answer. And is it positive? Yes, because it's to the right. So this one you would have to put a negative if the end result was to the left, because they didn't just say magnitude, they just said what is the force, and force is a vector, which means it has magnitude and direction, okay? So you would have to put the positive or negative sign on this, and it is positive, so I guess you don't have to really do anything because positive is assumed when you type it in. So yes, but still be mindful of that, okay? And so there's our answer. Hope all is well with you, and we will do another one soon.